Hey everyone, this video is about anti-differentiation, which is the opposite of taking a derivative, and the related concept of integration. I'm going to start with a weird looking question where we're told that f prime of x is equal to 2x and asked which of the following functions could be f of x. So we could solve this directly using brute force by taking the derivative of each of these options and finding what f prime is for each of them and seeing which one gives us 2x. So if I take the derivative of the first one, I have 1/2 multiplied by the derivative of x squared, so 1/2 multiplied by 2x. The 2's cancel and I get 1 times x. So it's not a. I'll try the next one. I take the derivative of 2, f prime of x is 0. 2 is a constant, its derivative is 0, so that's not it either. Remember, the goal is to get to 2x. Okay, now the next one, I take the derivative of x squared plus 7. 2 comes down, x to the power of 1, and then the derivative of 7 is 0. So I get my needed answer of 2x. So the correct option is C. We can check the other ones to see what happens when we take their derivatives. So for D, if we check that one, the 3 comes down, cancels the 1/3 in front. We get x squared plus 0, which is just x squared. That's wrong. And the last one, 3 to the x. Take the derivative of 3 to the x, we get 3 to the x times the ln of 3. It's an exponential function, so it follows the exponential derivative rule. So to do this brute force means taking the derivative of each of the available options and then just checking which one works. Now there's a faster way. We could ask the general question, what do you take the derivative of to get 2x? So I'll put that down on the side here. D by dx of what is equal to 2x? So that's the question. What's the what? And we already saw that the correct answer can be x squared plus 7, but there's other correct answers. What about f of x equals x squared plus 1? That works. The derivative of 1 is 0. F of x is equal to x squared minus 5. That's definitely going to work as well. The derivative of negative 5 is 0. It's going to disappear. We're just going to get 2x from the derivative of the x squared term. Or just x squared all by itself with no constant. So f of x is x squared. That definitely will give us, when we take its derivative, it'll give us a 2x. And in general, we can say that f of x is equal to x squared plus c, where c is an arbitrary constant. It's called a constant of integration, but for now I'll call it an arbitrary constant. Let's look at a tougher one. So we're told what the derivative is, and we're asked what is the original function. It's very important to read questions like this carefully to be able to distinguish a question like this from a question where we're asked to take a derivative. This is the reverse. This is the opposite. Here's the derivative. What was the function? So we can go through this list and take the derivative of each one. And it's not going to be very fun, but I'll go through it sequentially, just like the last one. So I'll take the first derivative of the first one. We have a chain rule. We have a function raised to a power. The 5 will come down, multiply by the 5 that's already in front. 25 times x squared plus 5 to the power 4. Multiplied by the derivative of the inside, because you're using a chain rule. So 2x. Derivative of x squared plus 5 is 2x plus 0. I'm just dropping the plus 0. And the next term has a product rule. So a, 50x squared, times the derivative of the second term, so b prime, 4 times x squared plus 5 to the power of 3, times 2x, plus the other part of the product rule, x squared plus 5 to the power of 4, multiplied by the derivative of 50x squared, which is 100x. And this is definitely wrong. we're not going to get anything canceling. This is not equal to 6x times x squared plus 5 to the power of 5. Most certainly not the case. Let's try the next one. So we're going to use, this is a w to the power of 6 function. The derivative is going to be 6w to the 5 times w prime. So we'll have 6 times x squared plus 5 to the power of 5 multiplied by the derivative of the inside. So multiplied by 2x. And I'll simplify this because this looks kind of close. This is going to be 12x times x squared plus 5 to the power of 5. So not quite. We want this to be a 6 in front, not a 12. So that's what the problem is. Now the next one. Now there's an x in front. What happens when we take the derivative? This is a times b. We need a product rule. So when I take the derivative here, I'll have a multiplied by the derivative of b, which we just did, 6 times x squared plus 5 to the power of 5, times the derivative of the inside, 2x, plus, now the second term times the derivative of the first, x squared plus 5 to the power of 6, multiplied by the derivative of x, which is 1. And this, likewise, is not our goal. It's not 6x times x squared plus 5 to the 5. Okay, now, next one, let's see what happens here. We'll take the derivative. This is 1/2 w to the power of 6. When we take the derivative, we'll have 1/2 times 6w to the 5 times w prime. So 1/2 times 6, so 3. And then w to the 5, x squared plus 5, all over 5. And then multiply by the derivative of the inside, so the w prime part, multiplied by 2x. Then we can simplify this. I can multiply the 3 by the 2x and gives us 6x times x squared plus 5, all raised to the power of 5. And that's it. That's our yes. And I invite you to try the next one. Confirm on your own that f prime of x is not equal to 6x times x squared plus 5 to the power of 5. Now what we're doing inside these two questions is we're kind of taking what's called an antiderivative. An antiderivative is when you're given the derivative of a function and asked what is the original function. Now what made this version of the problem easier is that we had choices, we had options to pick from. And we could check each one, we could confirm whether each case gave us the correct answer by taking its derivative. So using this brute force method. What we're going to learn inside this section is how to go from this, I'll use a different color. We want to go from this to this without having any options and without guessing, without massive trial and error. We want a systematic strategy for doing this. Now, for derivatives, the justification for derivatives was that the derivative of a function tells us about the rate of change of a function. And if we're doing optimization, finding where the rate of change is equal to 0, finding where the tangent line becomes horizontal, gives us potential locations for maxima and minima. So there's an easy geometric and applied reason why we care about taking derivatives of functions. The reverse, going backwards, doing antiderivatives, there's also a very concrete reason. It has tons of applications. We'll see soon what those applications are, but it is not as neat. And I'll save you from the proofs and the most theoretical parts of the formulation for the foundations of integration. I'll put it in a video later, but I won't put it inside this introductory week material. Okay, so this is the basic idea for an antiderivative, that you're told what the derivative of the function is, f prime of x. For example, you're told that it's 2x, and you're asked what is the original function. And from the first example we did, we know that the answer f of x equals x squared will work, since its derivative is equal to 2x. But we also know that x squared plus 7, or x squared plus 5, or x squared minus 3 will also work, because when we tack on that constant and take its derivative, that constant doesn't give any contribution to the derivative. Its derivative of that part is 0. So I called it, on the first example, I called it a, and actually I should go back and add that here. Well, I don't have to, but the most general answer would have a constant tacked onto it. This choice D did not have that. So it's a plus 0, but it could have a plus 3, a plus 7. I called it a arbitrary constant, and the formal name for it is it's called a constant of integration, because this process of taking an antiderivative is also called integration. So some more examples. What do you take the derivative of to get 3x squared? So at the beginning, the first time you see these, before you have formulas, you might try a few things. You might try 3 or 4 things until you nail the right one. But the what that you take the derivative of would be, say, f of x is equal to x cubed. Or f of x is equal to x cubed plus 7. Or more generally, f of x is x squared plus c. So the last one's called the general solution. And the other two are called particular solutions. And they would be particular solutions to a problem that has an extra piece of information. I'll show you what I mean with an example later on. The next problem, what do you take the derivative of to get x to the power of 4? So we can make a proposal. There's an approach. It's kind of like trial and error, where I'm going to guess the form. I'm going to guess it's like an ansatz or heuristic. There's different names for it, but I'm going to guess the form of the solution. I'm going to say f of x. Well, I know when I take the derivative of a polynomial function, the power is going to come down. So if my power after taking the derivative is 4, it means the old power has to be 5. So equals x power 5. However, when I take the derivative of x to the power 5, the 5 is going to come down in front. And I don't want the 5 in front. It's only x to the 4. It's not 5x to the 4. So how do I cancel it? How do I get rid of it? So let's look back at what we did for this one. There's a constant that was in front. The 1/2 in front, the 6 came down, it made a 3. A 2 came out of the derivative of the inside. The 2 times the 3 gave us a 6. So we needed to do something to compensate for the constant that came down when we took the derivative. And that thing that we have to do here is, if a 5 is going to come down, I want it to disappear, I need a 1 over 5 to cancel it out. So I need a 1 over 5 in front, 1 over 5 times x to the power 5, plus our arbitrary constant of integration. And then the next one's a little more confusing. What do you take the derivative of to get x to the power of negative 2? So I'll make a proposal. I'm going to propose, and then f of x is, so when we take the derivative, the power becomes lower. We subtract 1 from it. So if I start with power negative 1, when I take the derivative, the power will become negative 2, becomes 1 more negative. But then the coefficient in front will be wrong. So I'm going to show how do you do this checking process. Let's check. Let's confirm. F prime of x is negative 1 times x to the power of negative 2. So minus x to the power of negative 2, which is not positive x to the negative 2. There's an extra minus sign in front. So how do we fix it? So this is wrong. cross it out. Didn't pass our test. We tried to validate whether this proposal was correct. So now we're going to propose again f of x is equal to negative x to the power of negative 1 plus c. And that one you can confirm on your own. When you take the derivative of that, the negative 1 will come down. So you'll have negative times negative 1, so positive 1 times x to the power of negative 2, plus the derivative of a constant. Derivative of a constant is 0, so plus 0, which recovers exactly what we want, x to the power of negative 2. And we're doing things very backwards inside this course when it comes to the anti-differentiation in integral material. We're going to talk about the foundations later. We'll talk about the foundation of integration in terms of its geometry and as another topic. So part of this is just going to look like extra notation that we don't need, but there is a reason for it. You just have to trust me. We're going to write that capital F of x is the antiderivative of the function little f of x. And we're going to write that this operation is something that we can perform on a function. So we perform the antiderivative operation on the function little f of x. This is analogous to saying, d by dx of f of x. When we take the derivative of the function, we're doing something to the function. We're performing an operation on it and changing it into something else. Well, the operation, the way that we denote the antiderivative operation is with this squiggly symbol in front of the function. So the squiggly symbol in front is called an integral symbol. It's an S, actually. You take the letter S and you stretch it like this. You stretch it taller. That's the squiggly symbol in front. The S stands for sum, and you'll see why it's called a sum later. There's also another piece that's tacked on. So the business part of this expression is the f of x. That's the function that we're doing something to. The something that we're doing is the squiggly s. That's telling us we're going to take the antiderivative of it. The dx there is the same dx that appears in the derivative operation d by dx. And the derivative operation d by dx, the dx tells us that we're taking the derivative with respect to the x variable. So here the dx is just saying we're taking the antiderivative with respect to the x variable. So I'll label I'm going to label this squiggly symbol. So the squiggly means take the antiderivative of this, and then this last part with respect to the x variable. It's like a code. It's like a shorthand. The dx has a name. It's called the differential. It is its own thing. We can calculate differentials, and it's something that we'll do when we learn about a more advanced technique for integration. One thing to note is that you can never write the squiggly s symbol without a differential. So whenever you write the integral symbol, there has to be like a dx or a dt or a dw. There has to be d something. There has to be that thing there that tells us what we're taking the antiderivative with respect to. It has to indicate what the variable is, even if it's a single variable function. Okay, so again, we have this weird way to say, let's take the antiderivative of the function little f of x, and we're going to call it capital F of x. Now what this means is whatever our answer is, so the definition of a solution is if we take the derivative of our capital F of x, we will get little f of x back. That's how we know we did it right. This is kind of like a cycle. We start with an original function. If we take the antiderivative of it, it gives us a new function. Then if we take the derivative of that, it brings us back to the original. And we can keep doing that in a loop. The statement that the antiderivative of 2x equals x squared is identical in meaning, at least the level that we're talking about here in this course, is identical in meaning to the statement that the derivative of x squared is equal to 2x. The antiderivative of e to the x with respect to x equaling e to the x is identical to the statement that says the derivative of e to the x is also equal to e to the x. So that's the notation, an introduction to the idea, and what we'll look at next is we'll look at rules and shortcuts.